Maybe there is some microphone. Okay. Okay. Good afternoon and welcome again to the European Non-Associative Algebra seminar. I'm glad to introduce the speaker of today, Professor Přemysl Jedlička from the Czech University of Life Science, who is going to talk about non-degenerate involutive set-theoretic solutions of the Yang-Baxter equation of multi-permutation level 2. Please.
So thank you for the introduction and thank you for inviting me to this online meeting. And I'm going to talk about our collaboration with two ladies from Warsaw, namely Agata Pilitowska and Anna Zamojska-Dzienio from Warsaw Polytechnic University. And several years ago, we started to collaborate and we were studying quant laws, mainly medial quant laws. And then around 2018, we decided to focus on the solutions of the Yang-Baxter equation, which is something I'm going to define later. And this is really an interesting topic, mainly because there is an overlap of many different areas there, and actually people from different areas of algebra work there. People from group theory, from ring theory, or people from non-associative algebra like me. So each of us has a different point of view, and it makes this, for me, more interesting than if there were people that all share the same perspective. And what I'm going to emphasize is that many people, for studying these structures, use some ring-like structures named skew braces. And I'm not going to talk about them for two reasons. One reason is that somehow my starting point was quasi-group theory, and this is where I came from and what was my point of view. So not really ring theory, unlike most ring theories who are active there. Well, the second reason is that there shall be many definitions already. So I decided not to give that definition, that I don't need that much. But if you're interested in these skew braces, I'm pretty sure that in 2 weeks, when there will be a talk of Marzia Mazzotta, she will surely talk about it. So you can enjoy it. So as I said, my perspective was rather quasi-group theory. So when we started to look at this topic in 2018, what was our perspective? Well, first of all, what are these
I'm sorry, Przemysl, we cannot hear you. Can you check your microphones?
Přemysl? Excuse me. We cannot hear you.
Okay, so some of the problem was with it was too little, the microphone. Okay, so shall I start from the beginning or probably yes? So let's go back.
Yes. Yeah. From the next slide. Okay.
Okay, so what I was trying to say is that we have
again, we don't listen.
No.
Do you hear me?
Okay.
Yes.
Okay. Somehow it goes down the microphone. I don't know why. It is an equation that is named after two Nobel Prize holders, Yang and Baxter. And it is an equation that features a homomorphism of vector spaces, I mean tensor products of vector spaces, and is best drawn in this picture. And in full generality, finding homomorphism that satisfies this is quite difficult. So, as usually as when mathematicians find some problem difficult, they usually focus on some simplification or some particular case. So, for instance, a particular case here could be if this homomorphism sends a basis to a basis, then actually this homomorphism is described by a permutation of the basis. So this motivates this definition. We have just a set, which could be, for instance, a basis of a vector space. And we say that a set-theoretic solution is a mapping from a Cartesian product to the same product that satisfies such an equation. So the solution to simplify things even more, we say that such a solution is non-degenerate if, when we denoted it like this, these mappings sigma x and tau y are bijections. So from universal algebraic point of view, we can consider this to be a binary operation, and this a binary operation as well. So from universal point of view, we have two binary operations that satisfy some axioms that are not needed to be displayed here. And we want this to be a left quasi-group and this a right quasi-group. And this is actually how we were writing that we have a pair of one-sided quasi-groups. But slowly, when we understood the topic more and more, we started to take the notation that most researchers in this area agreed on. Our results are more understandable or more legible for the other people. Moreover, one more definition, since this is what we were talking about, such a solution is called involutive if this mapping is involutive. And this is again a simplification, because it turns out that in the case of an involutive solution, the other operation, tau, is uniquely determined by sigma, and hence we don't have a pair of one-sided quasi-groups. We have actually one-sided quasi-group to tackle. Okay, when we have an involutive solution, it was proved long ago that we can consider such a relation. Two elements are related if and only their permutations are the same. And then we can define operations on the classes of this equivalence. And it turns out that this equivalence is actually a congruence. That means these operations are well defined and give us if it is an involutive solution again, then we can again consider such a congruence and again until iteratively we may end up with one element algebra. And in this case, we say that such a solution is a multi-permutation solution of level, which is the level at which we end up with one element algebra. And my talk will be all about multi-permutation solutions of level 2. That means, in some sense, second least complicated solutions. Of course, the first least complicated solutions are those which are of level 1. But these which are of level 1 are very simple, since actually these sigmas have permutation, and these taus have to be another permutation. And in order to have an involutive permutation, it has to be actually the inverse permutations of this one. And such an involutive solution is called permutation solution or Lyubashenko solution, and it's actually the only example of solutions that are of level 1. And if such a solution happens to come from the identity permutation, we say that this solution is trivial 1. So these are solutions of level 1. This is not difficult to observe. So, okay, what about one step further? And actually, there is, before we can come to multi-permutation solution of level 2, there is one class of solutions that sits between solutions of level 1 and level 2, which also happens to be quite simple. And these are called two-reductive. Okay, what does it mean? In general, K-reductivity is an identity which looks quite ugly, but it actually means that if we perform sigmas iteratively, then at some point here we have x0 that is not present here. So at some point, these sigmas are no more relevant. And the level at which these sigmas are no more relevant is actually the level of reductivity. So we say K-reductive if it happens at level K plus 1. And it was observed a long time ago by already Gateva Ivan. Multi-permutation solution of level at most K minus 1, then it is necessary K-reductive. And if it's K-reductive, then it's necessary multi-permutation of level at most K. So as I said, this is a notion that sits somehow between the level and this is somehow why we started with two reductive solutions, since two reductive solutions are a special case of multi-permutation level 2, but they are more complicated than multi-permutation level 1. And actually, there are many examples of solutions where the level of reductivity and level of multi-permutation match. For instance, solutions that satisfy such a property, that means every element is a fixed point of at least one permutation. So for instance, those solutions that satisfies sigma xx equals x do satisfy this property, and for them the level of multi-permutation is actually the same as the level of reductivity. An important structure when studying quasi-groups is always permutation groups that act on these quasi-groups. So the same is for solutions. There are some permutation groups that act on these solutions. Naturally, we can consider, for instance, this group, which is generated by the permutation sigma, and such a group is called the permutation group, or if someone does not like this, you can call it the involutive Yang-Baxter group of the solution. And when I said then we can study the orbits of the action. And for instance, if we have a K-reductive solution, then actually every orbit is a subsolution. And it is a subsolution which is of multi-permutation level, which is small. Then for instance, if we have a two-reductive solution, then every orbit is a multi-permutation solution. And we know well how these multi-permutations level 1 solutions look like. So it is not really difficult to describe that we have one permutation for each of the orbits, but of course the orbits have some action on each other. But the two reductivity is somehow implies that this action is homogeneous. So, and moreover, it is equivalent to have to say that every of these permutations is actually an automorphism of the solution. To say that this two-reductive solution is multi-permutation of level at most 2, and tors are not only determined by sigmas, but they are, and that actually the retract is a trivial solution. And moreover, if we combine these two properties, since here if we replace sigma z, if we replace z by sigma xz, and we obtain sigma y sigma xz, but this is equal to this. So we obtain that every two-reductive involutive solution has a abelian permutation group. And whenever we have an abelian group acting on a set, the action of the abelian group is really easy to understand. We can factorize by the stabilizers and to do, which is not necessarily true for non-abelian permutation groups. But it is not the other way around. This is not true that whenever we have a abelian permutation group, that the two-reductive. An example is due to Rump. Rump was able to find a family of involutive solutions with their permutation groups cyclic, such that they are of arbitrary multi-permutation level. They had to have some multi-permutation level. It was proved by, and it was 2 Italians, but I don't know which were 2. So probably you can say me, but anyway, it was proved that it has to be some multi-permutation level, but arbitrary. And more.
Přemysl? Okay.
Yes.
Okay, please. Now it's okay. No,
Well, the problem is that somehow my microphone keeps switching off.
Okay, please go ahead. Okay.
I don't know why. So I look at it and I keep switching it on when it turns off.
Okay.
Okay, so we, that means me and Agata Pilitovska and Tanya Zamańska-Dzienio, were able to characterize that have the permutation cyclic and transitive. And it turned out that there are 3 invariants for such a solution, namely the size, then some number that divides the size and satisfies other properties, and also some number from this set. And these 3 parameters are in complete invariance for all solutions with such a property. And we can tell what is the multi-permutation level. It is the least case such that n divided. Okay, but this was something different. Let's go back to two-reductive solutions. these two reductive solutions have an abelian group acting on them. So if we look at all the orbits and stabilizers actually of the orbits, they are also abelian groups that can be factorized over. So actually we can construct it externally. We can construct the two reductive solutions starting from a bunch of abelian groups and a matrix of constants. And now the permutations are that simple. And moreover, we can really prescribe any abelian group in this construction. So, for instance, we can find a solution such that its permutation group is actually this prescribed abelian group. Even if it is infinite, huge, it's not a problem. So in the case of two reductive, it is quite easy since we have an abelian group acting on the set. So as I said, this was some step between multipermutation level 1 and multipermutation level 2. So what about others of multipermutation level 2? Excuse me. Before I do this, using this construction that I presented, we were able to construct all solutions that are two reductive. And as you can see on this table, there are really huge numbers of two reductive solutions. So they are actually, well, it comes from the fact that the nature of these solutions is rather combinatorial than algebraic. So this is why these numbers grow so huge. Actually, many of them are or can be constructed from Rex, and it was proved by Blackburn that there are, and if there are at least that many Rex, then of course there are at least that many two reductive involutive solutions, and that means solutions themselves. Of course, the question is, what about other solutions? Are there also that many, or there are less? We don't know. Okay, so these were two reductive solutions. Now, what about other solutions of multipermutation level 2, which are not two reductive? There is again some interesting group acting on the set, namely this group generated by sigma x sigma y inverse, which is called either the displacement group or the transvection group of the solution. And it was proved by Rump that such a group is a normal subgroup of the permutation group. And of course, the whole permutation group is a cyclic expansion of this normal subgroup. And moreover, Rump in the very same paper and independently we did, we proved that this normal subgroup happens to be abelian if our solution is a multipermutation level at most 2. And how did we prove this? We took the following trick. Let's consider it on an example. Well, let us have this 5 elements, and let us consider a solution which is defined like this. Sigma 1 is this, and sigma 3, sigma 4, sigma 5 this permutation. It is not difficult to check that it is too reductive. It is more difficult to check that it is actually, it is not too reductive, it is multi-permutation level 2. It is more difficult to check that it is a solution, but indeed it is. And it is more difficult to construct the permutation groups. The full permutation group consists of, well, it is group generated by these 3 permutations. So actually it has 6 elements and it is not commutative. But if we consider just the displacement group, then this transposition 1, 2 disappears. And we have just a 3-element group, which actually is commutative. So this is an example of the solution of multi-permutation level 2. And we see here on an example that really this displacement group is a normal abelian subgroup. And what was our proof that it's actually abelian? Well, if we have a solution of multi-permutation level 2, then we can, starting from this, construct a different solution using these permutations. We pick an element E and we take its the inverse of its permutation, and we construct a new solution with these permutations. It turns out that this new solution is on the same side, of course, and it is too reductive, and its displacement group is the same as its permutation group. Its permutation group is abelian since it is too reductive. So all these 3 groups are abelian. This was our proof. And vice versa, if we start from a too reductive solution and we pick some permutation that satisfies some property, then we end up with a solution of multi-permutation level 2, which is not necessarily involutive, necessarily too reductive. So this is a means how to construct all solutions of multi-permutation level 2. We start with a too reductive solution, and we know how to construct them all. And then we check all permutations, whether they satisfy this property or not. And then we can eventually construct all solutions of multi-permutation level 2. Well, in theory, in practice, there is a little problem. And the problem is the following. Consider the solutions we had before and how to construct some too reductive solution from it. Well, we can either choose number 1 as our fixed element, and then we obtain such a solution, or we can choose 3 to be our chosen element, and then we obtain with a completely different solution. We can clearly see that these solutions are not isomorphic, since here we have sigma 1 double prime of 1 for all the other elements. So actually, this solution is kind of idempotent. But this one not. So these two reductive solutions are not isomorphic. So the problem is that starting with two non-isomorphic two reductive solutions, we can construct isomorphic solutions. So we have no easy to check isomorphism criterion. And this is why we did not decide to construct all small examples of these solutions. But as a theoretic tool, it was very useful. It was very useful, for instance, to study indecomposable solutions. Indecomposable are those solutions where the permutation group is transitive. And if you remember that when we start with a k-reductive solution, then each orbit is of smaller multipermutation level, then actually, if we have a two-reductive solution, which is of multipermutation level 2, then it is necessarily decomposable. So if we are looking for indecomposable solutions of multipermutation level 2, there have to be not two reductive. This is with the proof. And there was this nice result of Castelli, Pinto. They were studying those involutive solutions of small sizes. I mean, for prime size, it was already known long before that there is only one up to isomorphism. So necessarily one step further. What about if we have size of product of two primes? How do these indecomposable look like? And it turned out that they are of multipermutation level 2. And actually, they were all all these solutions up to isomorphism. There is only one if these primes are different. And there are p plus one of such solutions if they are equal. And of course, when we are looking with my colleagues in Warsaw at this paper, it looked, the technique used there was really very technical. And we wondered, why didn't they our description of solutions of multipermutation level 2? They were aware of the result, they were citing us, but they didn't use it. So we said, okay, or they had their own means, so why not? But what if we use our theory? Are we able to reproduce their results? And well, up to the fact that we are multipermutation at most 2, and yes, we were able. We observed this fact. If we have a solution which is of multipermutation level at most 2, then actually the permutation group is generated by just 2 permutations, and the displacement group is generated by conjugates of 1 permutation. Well, if we are in a general situation, we have a non-abelian permutation group, then it doesn't mean really much. I mean a permutation group generated by two permutations. For instance, a symmetric group is generated by two permutations. It means little. But if we focus on abelian groups, finite abelian groups, then being finite and generated by two elements, it tells us a lot. And again, for the displacement group being generated by conjugates in an abelian group, it also means a lot. In the case of abelian groups, it simplifies a lot. Actually, it turns out that there are just three parameters to consider to construct all finite indecomposable solutions of multipermutation level 2. Two parameters are actually the size of the permutation group, and the third one is this R, which somehow happens to be there. And then every indecomposable solution can be written in such a way. And of course, these three parameters, N1, N2, and R, are complete invariants, meaning that different choices give non-isomorphic solutions, and they describe them all. So it looks a little bit weird, these properties. So let's check them on this case P times Q. So let us repeat these conditions. So we have three parameters, N1, N2, and R, that satisfies something like this. And our size happens to be P times Q, where P and Q are different. So N1 times N2 has to be PQ, N1 dividing N2, so it means N1 is 1, N2 is PQ. And R, if it is somewhere here, such that N2 divides N1 R squared, then R has to be 0. So there is only one. If our starting group is ZP times ZP, that means N1 is P and 2 is P. And if R satisfies this, then R has to be 0 as well. So there is only one option. And if N1 happens to be 1 and 2 happens to be P squared, then we can consider R to be any multiple of P. So we have P options. So altogether there are P plus 1 such solutions, confirming the result of Castelli, Pinto, and Rump. Okay, this was the abelian case, the less complicated one. And what about the more complicated non-abelian one? Well, actually, we were also able to obtain some description, because we knew that the permutation group is a cyclic extension of an abelian group. So if we the most general cyclic group, which is the free cyclic group, the most general abelian group, that means the free abelian group, then necessarily the permutation group has to be a homomorphic image of such a semi-direct product of abelian groups. And based on this homomorphism, we were able to find a solution, an infinite solution, which maps homomorphically to any multi-permutation solution which is indecomposable and of level 2. And not only that we said, okay, there is one universal solution that everyone gets mapped onto, but we were also able to characterize all the congruences of this one universal solution. That means, in the meaning that we were able to describe which congruences give us isomorphic solutions and which not. And again, we have some ingredients. There are 4 ingredients. The first ingredient is some integer that happens to appear somewhere. Actually, this integer is the index of the displacement group in the whole. So index of the displacement group in the whole permutation group. Second ingredient is some abelian group, which happens to be then isomorphic to the displacement group. Then an element from the group. So, okay, the first 3 ingredients is something that we can easily understand. And the 4th condition is quite complicated. We need to take a subgroup of, and now we don't need the free abelian group of rank infinity, since we are in finite case, so we can somehow factor out infinitely many coordinates and we can stack on m-1s. And okay, so we need to find a subgroup such that the quotient is isomorphic to our prescribed group. And these 4 invariants are again complete. That means that non-isomorphic solutions have different parameters. And the question is, if we want to count how many are there, the first 3 are easy to understand, but the 4th one, given an abelian group, can you compute how many subgroups satisfy this property? Well, if, for instance, the abelian group is a cyclic P group, then this question is equivalent to asking how many hyperplanes are there in a finite dimensional vector space over P. This is something that is fairly well understood. But if the abelian group is more complicated, then I don't know. But as I said, if we have A to be cyclic of prime size, for instance of size 2, then how many hyperplanes are there in a vector space of dimension m-1? Exponentially many. So it turned out that if we have a power of 2, then there are exponentially many indecomposable solutions just because of this fact. And using this construction, we were once again able to compute the numbers of those solutions up to isomorphism. And we were able to do it up to size 16. And that's all I wanted to say to you. And I'm sorry for the technical issues, but as I say, my microphone kept switching off, so I have to keep switching it on so that you can hear at least something. So excuse me if my talk was not that clear as I intended.
Okay, it was not your fault, of course. Thank you very much for the interesting talk. Are there any questions, comments, or remarks? Okay, if there are no questions, maybe there is a question from the chat. Please, Florin. Okay. Okay. Can you?
Non-associative structures, you mean?
Yeah. No,
well, they are non-associative structures.
Mm-hmm.
I mean, if you consider
Premise the microphone, please. Okay.
Actually, as I said in the beginning, the solutions is actually a pair of quasi-groups that are not semi-groups. I mean, there are rare cases where they are semi-groups, but usually they are not. So as binary structures, they are non-associative binary structures. Is it the question? Yes, thank you.
Okay. Okay. Any other questions? Okay. If not, let's thank Přemysl again.
Thank you.
Okay. So goodbye to everybody. See you again on next Monday at the usual time. Bye-bye.